This is a modern supercomputer. It contains many tens of thousands of individual high-performance processors connected by a very fast network. Each processor has a complex memory system for transporting data in and out. It is backed by disks and tapes that store so much data that if it were all in MP3 songs, to play through once would take 10,000 years. This is a complex system. It has a range of relevant spatial scales from micrometers, at which droplets of water nucleate around suspended particles, to thousands of kilometers, the range of mixing due to circulation. If we wish to study climate change, timescales must range from centuries down to milliseconds. Here is another complex system. Near the combustion zone of this burner, literally hundreds of chemical species perform a complex kinetic dance with each other while being whisked around in a turbulent flow. Among the many products are microscopic soot particles, which, if released into the atmosphere, form nucleation sites for the water droplets that are major players in the climate system. Here is yet another complex system. This compact, efficient pump works without interruption for up to a century on surprisingly little power. Its tissues are made up of fibers with intricately woven orientation that coordinate their contractions with the precision of instruments in a symphony orchestra to squeeze oxygen-depleted blood through the tortuous tubes of the lungs between which it is nestled, and simultaneously to send the returning oxygenated blood to the furthest parts of the body. It is controlled over a range of operating conditions by small, spatially distributed pulses of electric current. Thanks for joining me in a brief look at computational science and engineering at KAUST. I am David Keyes, the director of the Extreme Computing Research Center. Our challenge is to simulate complex systems, like a planetary atmosphere or ocean, a combustion burner, or a heart, on the complex system of the computer. These are prospects passionately pursued by KAUST scientists, such as my colleagues Gera Stenchikov, whose model of the global atmosphere is here, or Ibrahim Hotit, who is walking across his model of the Red Sea. They are scientists seeking nature's secrets, engineers striving for efficient design, computer scientists creating amazing tools, and applied mathematicians like myself, seeking to describe the natural world to the virtual world. Computational science and engineering lives at the intersection of three areas: mathematics, computer science, and any application. The links between the natural and the virtual worlds are mathematical models, algorithms, and computer code. In our center, we strive to span the huge gap between the natural and virtual worlds, with solutions expressed in equations and various levels of software that provide clean interfaces on each end of the link, so that physicists or physicians can apply their special domain knowledge, computer engineers can supply their systems expertise, and large, diverse teams can work together to understand or design while riding the wave of increasing computational power. A supercomputer is much more than an arithmetic device. It is a storage device par excellence. Much of this processing chip from Shaheen consists of caches of memory, or communication channels to vastly more memory millimeters away. Computers can hold and access in parallel vast troves of data from natural observations, controlled laboratory experiments, or computational simulations. These data, interpreted through the right statistical models, have enormous predictive power by themselves, independent of any time-honored physical models, such as the conservation of mass, momentum, or energy. The ultimate glory of the supercomputer is its ability to combine data and simulation. Predictions from data alone and predictions from models that lack reliable inputs are prone to error. But data and models combined with the right mathematics can expose likely errors and reduce them. Simulation and experiment are complementary to each other. Experiments suffer many difficulties. Some experiments we would like to perform with living organisms may be deemed unethical. Some, from the fact that we get just one chance, like with the environment, lack a control comparison. Others are inaccessible, like supernovae, or prohibited by treaty, like thermonuclear explosions. Some are difficult to instrument in as many places and with as much time resolution as we would like. Other experiments are becoming too expensive, such as the International Thermonuclear Experimental Reactor, ITER, a controlled fusion reactor to which about half of the world's taxpayers contribute, whose cost is now over $22 billion and growing. Simulation keeps its hands-off nature, but in the words of physicist James Langer, it provides a window through which we can observe the natural world in exquisite detail. Simulation is also a time machine, not possible in the real world, speeding up or slowing down time. Certification of a new nuclear fuel may require a 20-year test in a power plant, but it can be aged artificially quickly in a computer. A protein that folds in a millisecond can be visualized frame by frame over minutes to give biologists insight into the mechanism. But for all of the potential of computer simulations, they can never replace experiments because their models and their input data may always be uncertain. The great complementarity of simulation and experiment is that simulations can narrow down the range of expensive and time-consuming experiments that need to be done to verify results. The computer is perhaps the most universal of scientific instruments. A DNA sequencer is for biologists, a spectrometer for chemists, an atom-smashing accelerator for physicists, a telescope for astronomers, and a sea vessel for oceanographers. But a powerful computer serves all comers, and these general-purpose computers are becoming spectacularly powerful. When I graduated as an engineer from Princeton in 1978, just introduced computers like the VAX 11780 delivered a then impressive 1 megaflops, or millions of floating point operations per second. By 1988, organizations for which I consulted, like NASA and the US Department of Energy, had Cray YMP systems capable of 1 billion or 10 to the power 9 floating point operations per second, 1 gigaflops. Steady progress in parallel computing yielded the world's first teraflop system, ASCII Red from Intel, delivering 1 trillion operations per second in 1998. In 2008, IBM delivered the world's first system capable of a petaflops, the number of operations per second being represented as a 1 followed by 15 zeros. This pace of improvement by a factor of 1,000 every 10 years, or 1 million every 20 years, since the improvements are multiplicative, is unheard of in any other technology. If a factor of 1 million in speed had been realized in the commercial aviation industry from a point 20 years ago, the flight from Los Angeles to Jeddah would today be over in 1/20th of a second. Of course, without other improvements, we would still spend 2 hours at the airport, and the problem of I/O remains like that as computer processing speeds up, too. If the factor of improvement in storage density from the IT industry had been realized in the publishing industry, we could keep all of the text of the Library of Congress at arm's length in our offices. And if improvements in the power per unit cost from the supercomputing industry had come in higher education, annual tuition, room and board at a private college in the USA today would cost about 20 cents. Any commodity which on a regular and predictable basis falls dramatically in price attracts new uses as it becomes cheaper and displaces competition. Consider the palm date. Delicious. At today's retail price of 64 Saudi riyals per kilogram, they are reserved for use as delicacies. If, however, we were able to predict that within 3 years, their price would drop to just 16 riyals per kilo, recipe books would be rewritten to substitute date sugar for all other sugars. If we knew that after an additional 3 years, the price would drop by another factor to 4 riyals per kilo, we would figure out how to use dates as a commodity organic feedstock for biopolymers, plastics, etc. Continuing this trend, if by 12 years from now dates would cost just 1 riyal per kilo, we would re-engineer furnaces to burn dates as fuel. And if in 3 more years we knew that dates would cost just 25 hilalas per kilo, we would use them in place of asphalt in paving roads. The cost of computing has been on a curve much better than this fictional date curve for over 2 decades, and the economy has absorbed every advance in improved performance or improved productivity. Today's car, for instance, is a parallel computer with safety, maintenance, navigation, security, and entertainment services unimagined 2 decades ago, built by robots that are far more precise welders and bolters than humans. The animated movies like Avatar or Frozen, streaming in the back seat of your car, were rendered by a supercomputer. Your cell phone has more power than the supercomputer on which researchers designed that car's predecessor 20 years ago. Nowadays, long after communications, Hollywood, banking, medicine, manufacturing, and all other facets of society have hitched rides on computing's power, dramatic price reductions, scientists and engineers, pretty conservative people as a whole, are finally making room for simulation as a reproducible and error-quantified tool of discovery. This trend has been enshrined in research programs, such as the Scientific Discovery Through Advanced Computing program of the U.S. Department of Energy. I led a multi-institutional, $3 million per year SIDAC Scalable Algorithms project for 10 years, and we have reproduced the philosophy of that program in the Extreme Computing Research Center at KAUST. We want to deliver a sound return on investment on KAUST's supercomputers and make today's commodity supercomputing at the petascale achievable by scientists and engineers who are not expert at computing, but who have come to KAUST because they are expert at something else that is critical to our mission, like chemistry or chemical engineering. Let's see. 1978, a few megaflops. 1988, the first achieved gigaflops. 1998, the first teraflops. 2008, the first petaflops. Always a factor of 1,000, right on schedule, like the new moon in the night sky. This technological progress was enabled by a combination of Moore's law for miniaturizing superconductor devices and parallelism, putting more devices together in a single computer. Extrapolating the trend line, I wish I could tell you that KAUST expects to install a 1 exaflops computer capable of 10 to the power 18 operations per second in 2018. However, I cannot. Unfortunately, the pace of miniaturization is slowing down due to many physical limitations, from the wavelength of chip lithography to the ability to dissipate the heat generated from dense packed transistors flipping at a gigahertz. The straight path is ending. Until carbon nanotube devices, DNA-based devices, quantum devices, or some other experimental technology is able to put us on an entirely new path, we will probably be limited to individual processors no faster than a few gigahertz, like your laptop. To achieve 10 to the power 18 flops, with workers that deliver 10 to the power 9 flops each, we will need 1 billion such workers. If these workers need to synchronize, they cannot be too spread out, since electronic or optical pulses travel no faster than about 1/3 of a meter in a nanosecond. This distance, which is the time it takes a 1 gigaflops processor to complete one arithmetic operation and to start in on the next. So 1 billion processors cannot globally synchronize at large distances without lying idle for thousands or more operations. Also, when you depend on too many workers, you cannot guarantee a very long interval before one gets sick or drops out. Or maybe, worse, the worker stays on the job but begins to do unreliable work. As a result, most of the algorithms that scientists and engineers use today will have to be replaced with counterparts that are less synchronous and fault-tolerant. The latter means that algorithms can detect hardware failure and correct it without delaying all workers. Rewriting a world full of software for simulation of climate, combustion, cardiology, and so forth, for new massively parallel, synchronization-sensitive, and unreliable hardware is a challenge identified by the G8 countries in the International Exascale Software Project. We need new algorithms, new parallel programming models, and new languages to express the new algorithms. KAUST scientists have been involved since the beginning. We are evolving existing algorithms and creating new ones for this new computing environment. We are learning how to put less pressure on the relatively slower per processor memory systems of future computers. We are learning how to synchronize and communicate less while still completing a task accurately. And we are seeking to build in resilience to hardware faults. But we are not simply seeking to move existing applications to new hardware environments. The next factor of 1000 in hardware performance opens up dramatic new vistas for scientific prediction and engineering design. Remember that atmospheric model? Yes, we want to run it with fine resolution for longer periods and with all of the detailed physics that we know. But we also want to do many other things that are made possible by that coveted next factor of 1000 at exascale. You see these predicted hurricane tracks? Which one is right? We want to test sensitivity of key quantities of interest from the model with respect to model inputs that we do not know precisely. We also want to take measurements from weather stations and satellites and assimilate these into the model. These objectives require wrapping layers of loops around the existing models, which have to be executed numerous times and their outputs compared. Finally, after we have validated and verified our improved atmospheric model, say, we want to hook it up with other similarly qualified models of the world ocean, the polar ice sheets, the terrestrial vegetation, and so forth. Will these ambitions soak up the generous seeming factor of 1000? Actually, they will soak up much more, so that scientists will be greedy for zettaflops long before exaflops are routine. Yes, you guessed it. One zettaflops is 10 to the power 21 floating point operations per second. Practical zettaflops for general purpose computing will arrive only after my working lifetime is over, however. So we also need to work on what are called reduced order models. These models are less computationally demanding, but more mathematically sophisticated than a typical extreme scale model. They are capable of predicting quantities of interest to adequate accuracy without having to predict everything to high accuracy first. When we succeed in this last step, we will be able to fit a significant amount of leading-edge science onto more modest computational resources. But we will always need leading-edge computing resources to bootstrap us up to this higher level of understanding. It seems that my coworkers will always be part of a full employment program. You should join us. So, what is a typical project in the ECRC today? Do we need to wait for a billion processor computer to do our work? Fortunately, no. The first billion processor computer will be assembled from advanced processing units, or APUs, that combine on a single chip a mixture of multi-threaded graphics processing units, or GPUs, with many-core central processing units, or CPUs. Representative GPU and many-core CPUs are here today, so we can explore and demonstrate how to use them. KAUST authored software for NVIDIA GPUs is already faster today than previously available routines, and has been incorporated into manufacturer NVIDIA's own library distributions. In other cases, our software is not very much faster on today's hardware, but it consumes less memory per flop, or permits many more concurrent flops. Therefore, we are certain that these algorithmic adaptations will sing on tomorrow's hardware. When KAUST was launched in June 2009, our supercomputer Shaheen put the Middle East on the map in supercomputing. At that time, only the United States and Germany possessed faster supercomputers. After 5 years, the same Shaheen slipped back in the rankings as computers have advanced in power by more than an order of magnitude on their still exponentially growing, though slowing, path to the exascale. During its 6th year, KAUST placed into service a new supercomputer 25 times faster than the first, which catapulted the university back into the top 20 rankings worldwide. Our colleagues in climate, combustion, and chemistry, and other fields will take advantage of a certain factor of performance improvement simply by compiling their code on Shaheen 2. But to take full advantage of the next generation's capability, KAUST's Extreme Computing Research Center will be there with them, poking and probing, and exploring how to make their codes sing an even sweeter tune, right away, and then when we reach exascale, which is extreme enough for now.